Hi, good morning. My name is Hugh Leather from Meta AI, and I'm going to be talking to you a little bit about how to do auto-tuning with the CompilerGym. Hopefully you've watched Chris's bit of the talks already, and so you probably understand a good deal of what's going on in the CompilerGym already. Today's talk, I'm going to very briefly talk to you about what auto-tuning is, in case you haven't come across it before. And then I will show you using the CompilerGym Shell how we can first of all explore many of the capabilities of the gym and also do some very simple auto-tuning searches using LLVM. And then we'll come back and very briefly do a little hill climbing search in Python in a Colab notebook. Okay, so what is auto-tuning? Well, it's quite a simple process really that searches for the best compilation strategy to apply to a program. So we start with a program down here written in some language, and we ask the compiler, say LLVM or GCC, to compile it, but not in the way that it would do by its default, with some particular compilation flags or settings, or even fine-grained structure of the compilation that we apply to it. Now in the gym at the moment we have LLVM and GCC, both of which to some extent use command line flags. There is also loop tool, which goes deeper inside the compiler and exposes more fine-grained opportunities and decisions to the auto-tuning search. Your compiler produces an executable, or maybe falls over and gives an error, and then you can find out how good this executable is, how good these set of compilation flags or compilation settings are, by running it through a machine if you're looking for execution time, or if you are not using execution time, perhaps as we're going to today, using code size, then you don't need to run it on the machine, but you do need to work out how well the compiler did. You pass this information back into some search routine, which chooses the new compilation strategy to try based on what it has seen so far. And this process continues until you get bored of running your search, or the search says that it can do no better, and then you report the best compilation settings you can for the program that you've been trying to optimize. So, a really super simple technique. There are, of course, machine learning versions of this where the search is replaced by or augmented by a machine learning technique, and in a later part of the talk we'll look with Mustafa at using reinforcement learning to do just that. But for this part of the talk, no machine learning, just straightforward search. Okay, so now I'm going to show you the CompilerGym Shell. The advantage of the CompilerGym Shell is that you don't need to write any code. It has auto-completion, and it makes exploring the capabilities of CompilerGym a little bit easier than it is using Python. The downside of it, though, is that unfortunately you're going to have to install it. So we are going to be online in the Zoom call, and if you have any trouble doing the installation, then please come and give us a shout, and we'll see what we can do to help you fix your installation problems. So here is my existing shell, my bash shell, and I'm going to type in the command to install CompilerGym. It's quite simply just use pip install CompilerGym, the nice and easiest one-line install that I think you could probably wish for. Well done to Chris and a few others for making that as easy as it is. You may find that you don't have pip on your system, or in fact Python, in which case please try and install Python first, and if you struggle with any of this, if you type this in and you get errors, then come and talk to us on the Zoom call. I will also say that as we go through these steps in the video, you may want to pause regularly and follow through yourself on your own machine. Okay, so I type in pip install, and because I have actually already installed it, it's gone quite quickly. It's not much slower than that if you are doing it for the first time, but it has succeeded. So I can just clear that screen, give that a go, and hopefully you should be ready and set up to actually install, to start using the shell. Now what we're going to do is we're going to ask the CompilerGym to start our shell for us. The way we do that is by calling Python with a particular module. The module we're going to use is this program here, which is the manual environment, which is a very long-winded way of saying shell for CompilerGym. Beg your pardon. We also need to tell it which environment we want to do. There are loop tool, LLVM, and GCC. Today we're just going to look at LLVM. So we give it this environment name, LLVM version 0. It's not version 0 of LLVM, it's version 0 of CompilerGym's version of code that calls LLVM. Once you put that in, when you press return, hopefully, if all has gone well, then you should get a prompt like this. If it has not gone well, then, as I say, we're there on Zoom. If you can do that, that's great. If it's after the tutorial is over, then you can find lots of help on the website that Chris has created, and hopefully that will help you to sort things out. So good luck with that. All right, well, let's look at what we get here. We get some not terribly interesting welcome messages and so forth, and then we get this prompt, the first bit of which is not very interesting, but this bit here actually tells us some useful information. And what it tells us is that the program we are currently optimizing is from the CBench benchmark suite and version 1 of it for us, and that the benchmark that we are looking at is the quicksort benchmark from that benchmark suite. Okay, well, that's great. So we'll have a look at that in a moment. But before we do, let's see what kind of commands we can get from the shell. If we type in help, we'll see a list of commands like this. Now, we have some things we're going to look at. We've got things like list datasets. Now, a dataset is what you may think of as a benchmark suite. So we can type in list and tab to get auto-completion, and D and tab to get auto-completion, and we'll list the benchmark suites. So here we are, we see our benchmark suite. These are URLs. You'll notice that most of them are these benchmark suites, which are sort of finite sets of benchmarks. And then we have these generators, which can effectively generate an infinite number of different programs for you. Well, 4 billion or so. Quite a lot. Okay, so those are our data sets. We can also list our benchmarks. If we do that, we get a very large list. The reason why it's a very large list is that things like AngerBench, which is an ordinary benchmark suite, have something like 1 million benchmarks in them, and we didn't think you'd like to see them all. And then in addition, we've got these generators which generate lots and lots of benchmarks for you as well. So quite a lot of those, but because we've got command completion, then tab completion, then we can still go through these quite easily. Get our help back up. Let's try changing the benchmark that we're on. So we will set the benchmark, and as I say, you should have a go at doing these yourselves. And we're going to use the CBench benchmark suite. CBench. I tab completed that because I couldn't remember which way around it was. And I can't remember what the things in there are, so I tab and it shows me. And I'm going to use Susan because why not? Okay. So it will load that up and compile it for us and reset everything to make it nice and useful for us. Okay, great. Now, hopefully you remember from Chris's talk that because we are doing this in a reinforcement learning style of environment, then we have 3 things of interest to us. These are actions, which apply transformations to the state, or the program in our case, that we are looking at. Observations, which tell us things about the state of the program after those actions have been applied. And rewards, which tell us how good the current state of the program is. So we will have a look at a couple of those by listing what we have. So first of all, we'll list our actions. And there we go. We've got lots of different actions. These are actually the same strings that you would put into the to LLVM's opt tool. We thought it would be nice and easy for you to do that, to look at it that way. So there we go. And we can, for example, apply an action with the action command and writing the name of the action like that. Those also command complete. Oh, now it's told us that no effect. So LLVM doesn't think that this pass did anything to Susan. We see reward 0, but we'll come back to that in a little bit. We can do multiple of these in one go. If I put a minus sign in there, and you'll see those are both applied. Okay, so we've got some actions. Our reward is 0, so that's a bit odd. I wonder what will happen if we ask for the reward. And unknown reward, we don't have a reward. We could instead auto-complete that. One that we're going to look at is instruction count. Okay, there we go. We get an instruction count. Now it's odd because we'd kind of like to know how many instructions there are in Susan. And the problem we have is that when we just call the reward, it tells us the current difference in the instruction count. If I want to see what the actual actual instruction count is, I can do the same thing with instruction count, and it will tell me that Susan has about 13,000 instructions in the IR. Great. Okay. So we've got that, and we'd like to be able to see what kind of actions we've applied so far. This we can do by typing in stack. Stack will show us the actions that we've applied and the rewards that we have accumulated so far. You'll notice that there is this slightly odd dash there, which doesn't mean that no reward has accumulated. It means that we have not told it what our default reward is. As you will have noticed, there are several. So sometimes when we are printing things, we can have a default reward, and if we set that to our IR instruction count, then when we now type stack, we will see that we get zeros in there, which is more useful to us. If I apply an action that I know will do something, like mem to reg, we'll see that now, if I show my stack, big button, we'll see that we have a great reward that we have achieved by reducing the code size. And we can just check that we have. In fact, I'll just say that I can go through the previous things that I've done with up and down, and now we'll notice that whilst we did have about 13,000 for the instruction count, we now have a little less than 8,000, which is great, just by doing mem to reg. Okay, so I could come along and try different actions, and I could do partially inline libcalls, and I could keep doing that to search my space. Sometimes you just want to try something a bit random. If you type in action and do a dash, then it will randomly choose an action for you. Okay? And if you just press return will do whatever the last command was, and so we can do lots and lots of different things like that. Okay. And if I now look at what the stack says, we will notice that we have some cumulative rewards here where we're doing quite well. We had some things that did worse, made things worse for us. These made it worse. Oh god, this one, reg to mem, made it much, much worse. And then things started to get better again up here. Right, so we've had lots of these things that have gone. We probably don't want all of those. We probably would like to get rid of anything that didn't have an effect or had a negative effect. In the gym, we can do that by typing in simplify stack. And what that will do is go and take out all of those useless or negative actions. However, because now not all actions are done, and some of these passes do have an effect, even if it doesn't produce a reward, it may change what future rewards are available. And so the shell will tell you that something has changed in between the last two times that you did it. Sometimes you may even find that something which had a positive reward ends up with a negative reward, but not in this particular case. Okay, so there we show our stack. It has much reduced. We see that there still is a zero reward thing in here. It has a positive reward previously, but with this new ordering, it has got only a zero reward. Okay, so that's enabled us essentially to do a random search through the space just by holding down the return key after we've pressed action dash, and then do some small investigations on the stack of actions as well. Oh, we can undo an action, for example, by pressing back, and then that will show you what has happened. You'll notice that that action number 7 has now disappeared. Okay, so we've had a look at that. Let's see what else we can do. Well, we could do these searches randomly, but we might want to go and find what the best actions are. So we can, I'm going to reset to bring us back to the beginning for this, this benchmark. You will see that if I type stack, we've cleared all the actions. If I do try all actions, it will try each of the actions and tell us how well they would do if we did them, leaving us in the same state that we were before we started trying all the actions. So here we see them listed in worst at the bottom, all the way up to the best at the top, and you'll see that SROA looks like the best thing for us to do. So we could then do that action and then call try all actions and do that again, and we'd be able to have a greedy search. It is a little simpler to do that in a shell because you can actually just type greedy and give it a number of steps that you want to do. We'll just leave it and just do one step of that at the moment. And it will try all of those actions, and then it will apply the best of those. And if I look at the stack, you'll see that we have applied that one action. And I can do for example, 2 steps of that by giving a number after greedy. It takes a little while. Applying quite a lot of passes to this program, and let's have a look at what we've got left. So we've got 7,500 fewer instructions just in 3 steps, which is quite nice. You could have greedy go on for quite a long time if you wanted, but we can look at what other things we have in the gym. The other search that is built in is hill climbing, which is simply going to randomly apply actions, accepting any that make the situation better and reverting any that don't. So we'll do one hill climbing step, and you'll see that it randomly does one, and we've accepted this because we had a positive reward, so it accepts it. And if we do that, we'll see that that is now on there. If we type in hill climbing and put in a number, let's do 50, then it will try to improve things 50 times, very slowly. And there we go. If we now look at our stack, we will see that it accepted some of those, and we've improved matters a little bit by doing our random search. Okay, so that is the CompilerGym Shell. It's a very useful tool for you to be able to work out what's going on. If you type help for any of these commands, you can get more information about them, and we can exit to get out. Okay, so that's the CompilerGym Shell. We've done a little bit of auto tuning. Now we're going to move over to the Colab notebook and have a look at doing some hill climbing. So I'm really just going to talk you through what this code does. It's also commented, so you can probably see that you could probably work it out for yourself. So we're going to start by doing hill climbing, which, as you've seen, essentially randomly applies some action, and if that action doesn't give you a good reward, then it just undoes it, and it'll keep doing that for some number of steps. So let's have a look at how we do that in the gym in Colab. We start by installing the gym through this little bash command type thing up there. It says do that in bash. And then we need to import the namespace of the gym. If you're familiar with Python, all this will be fairly straightforward to you. We then need to create an environment. We're going to use LLVM for this one. And that is that contains our benchmark and all the optimizations, and provides us the ability to be able to make those actions that we did before in the shell. We're going to use the same benchmark that we had before, so cbench Susan, and we do that by resetting the environment and telling it which benchmark we want to use. We then we can set the observation space and the reward space, so that we can, as we're doing our search, we can find out how much better or worse things have got. And we'll just print out here where we currently are with that for this program. So here you'll see this F is asking it to do string interpolation, and you can see in there we're interpolating with the contents of that, and it says to get the particular observation, which is this one, from the program. Okay, we're going to do just 100 steps of hill climbing, which means that we will need to do some for loop over that. And in order to do our actual hill climbing step, we need to be able to undo an action. Now the CompilerGym doesn't immediately provide an undo capability for you, but what it does allow you to do is to essentially copy the environment, which is done by a fork, and you can then choose which one of those environments, the original or the newly forked one, you wish to keep. So here we've got our candidate that we fork from the environment, and we can make changes to the candidate without affecting the original env. We will choose a random action, and we'll do that by getting the action space from the candidate and asking it to randomly sample an action for us. Could do this with using random number generators and stuff, but the gym makes it very easy for you, so why not use the easy way? We then apply that action to the candidate, and that will return us several bits of information. It will return to us the current IR instruction count, of the sort of global one, the reward that the current step has created, whether based on just this single step, so did that make the code better or worse. It will be positive if it made the code better, negative if it made it worse. Did this make us fall over yet, and therefore have to stop, and some other information which neither of these two are particularly interesting to us at the moment. We're going to print a bunch of information about those so that we know which action we chose, what its name was, which you'll see I can get from the names list in the action space. And then we'll explain what reward we get and tell us whether we are going to accept this, because we'll only accept it if the reward is greater than 0. And now we need to choose which of the two environments we will have, we'll keep. So if the reward is less than or equal to 0, then this action didn't help us. So we can just get rid of the candidate and throw it away. And if it did make things better, then we can get rid of the original environment and replace it with the candidate. So let's quickly run that, and hopefully this code that I've just written for you will work. And there we go. So we're installing the shell, installing the gym, and then you'll notice, you will notice that we found out the total number of instructions at the start, and now we go through our hill climbing. Occasionally an action will call something to fall over, but the gym very nicely just picks up and carries on regardless. So here we go at the end. How well did we do? We got down to a total number of instructions of 6,120, which is a pretty good optimization given that it originally started at 13,000. Okay, thank you very much. That's this part of the tutorial. I hope you enjoyed that and had a go at doing these things yourself. And I think you'll now have with Mustafa some reinforcement learning to do. Thank you very much.